All right, welcome back. And so here's what we said. Earlier we said by definition, let's let dw in one dimension would be f times dx. And then we said w will equal to the integral of f dx. And this w is equal to the change in kinetic energy. So the kinetic energy at the end minus the kinetic energy at the beginning. And we integrated this, and we said this is equal to, let's say from x1 to x2, this was u1, u at x1 minus u at x2, this integral here, assuming we can do it. I will show you when this will not work. Equal to k2 minus k1, and this u is defined such that f is equal to negative du dx, okay, by definition. And so it's just u is any antiderivative of f, any antiderivative. Because remember, antiderivatives are not unique. They are generic up to a certain constant. Right? For example, the integral of x is 1/2 x squared plus some constant. All right. So you can always add an arbitrary constant. So we call this U here the potential energy. It's called potential energy. So let's see, what's the potential energy, what's the work done by a spring? So here is a spring. It's on a natural position here, right? And I'm going to expand our spring. Expand our spring by this is x initial, or x1 equal to 0, and this is x2 just x, all right? I'm going to expand the spring. So how much work did the spring do? Well, as you pull this way, the spring is applying a force in this direction, right? And remember, the force of the spring is proportional to how far you stretch it. But if you stretch it to the right, the spring is pulling you to the left, so there is this minus sign, and this is called Hooke's law. Hooke's law. Hooke's law. In other words, if you compress the spring, if you're on this other side of the equilibrium, the spring would be pushing you to the right. So what's the work done by the spring as we stretch it by a distance x? Well, the work would be the integral from x1 to x2 of f dx, but f is negative kx, so you get the integral x1 to x2 minus kx dx, and so this becomes, you integrate this, becomes minus 1/2 kx squared from x1 to x2, and so this becomes 1/2 k, or negative 1/2. You can switch the limits and it becomes positive, so I'll just write it as positive. 1/2 kx1 squared minus 1/2 kx2 squared. Okay. You remember, like, if you have the integral of x1 to x2 of f of x dx, this is the same as negative the integral of from x2 to x1 of f of x dx. That's what I basically did there. Okay? And so that's the work done by a spring. Okay? So what's the potential energy stored in a spring? What's the potential energy associated with a spring? Well, we said the force is the derivative is equal to negative du dx. So what would u be? U, if f is minus du dx, Okay? So something, when you take the derivative of something, you get kx with a minus sign. When you take the take the derivative of something and put a minus sign in front of it, gives you minus kx. What could that thing be? Well, it's only u will equal to 1/2 kx squared plus a constant. I will ignore the constant. This is one antiderivative. So we say this is the potential energy stored in a spring. So you have, you can take the derivative of this. What's the derivative of u? Would be kx, but F is equal to negative du dx, and so it will be negative kx. So that works great. Okay. So, all right, looks good. I want to just look at a couple of examples here before I move to higher dimensions. So before we move to the more general version of this work energy theorem, potential energy, I would like to discuss a couple examples here. So we have a spring here, and the spring is tied to a mass, 2 kilograms, and the mass is resting on the floor, and the coefficient of static friction between the floor and the mass is 0.6. And we're given that the force constant of the spring is 15 newtons per meter. Okay. And the question is, I want to come along while the spring is attached to the mass, and I will start pulling on the spring. I will pull on it until the mass starts to move, until the spring is stretched by an amount x. So how far should we pull to get the mass to move? Right? You start stretching the spring, eventually the mass will break loose and start moving. How far? Well, as you start pulling the spring on this side, the spring will also pull on the mass on this side, right? Remember, springs always pull on both sides. You have to tie it to one end. So the spring is pulling on this mass with a certain force. Why doesn't the mass move? Well, let's draw the free body diagram for the mass. Here is the mass. There is, of course, the normal force. There is mg. There is the force of the spring. I'll call it Fs. And then there is the force of static friction. Sp for spring. Force of the spring, the force of static friction. And as you remember, force of static friction does not take a single value. It takes a range of values between 0 to a maximum value. When the force that the spring applies on this mass to the right is equal to the force of static friction that's opposing the starting of the motion, then the object will start to move. So the object will move, the mass will start to move when the force of the spring ends up being equal to the force of static friction, the maximum value. When you reach that maximum value, or go beyond it by just a little bit, then it will start moving. So when these two, that's the critical moment, when these two are equal. Now the force of static friction, the maximum, will equal to mu s times the normal force. The force of the spring, the force that the spring applies on the mass, what would it be? Well, if you pull the spring to the right, the spring will pull you to the left. But on this end, the spring is pulling the mass to the right, because the mass is pulling the spring to the left. Okay? That's why the spring is not moving. The reason it didn't move, if you pull it this way, why doesn't the spring accelerate? Because there is a force on it on the opposite end. Because if you just consider the spring by itself, then you're pulling it this way. Why doesn't the spring itself start to move? If you just had a spring that's not tied to anything, you pull it to the right, it will just move. So it has to be being pulled by the mass. So how much is that force? Well, remember, it is equal to kx. You might say, well, we said minus kx earlier. Well, it's minus kx on this end, but and here it's to the right, so it's positive kx. Now, so I have kx equal to mu s. What's the normal force? In the y direction, the normal force is simply equal to mg, because there's no motion in the y direction, so it's mg. And so x will equal to mu s mg divided by k. Mu s is 0.6 in this problem. It's given to us. The mass is 2 kilograms. G is 9.8, and K is 50. It's 50. And so we get, well, we need a calculator for it. How far should we stretch it? It would be 0.6 times 0.2 times 9.8, and you divide by 50. You get 0.024, basically, 0.024. You get x equal to 0.024 meters. That's approximately 2.4 centimeters. 2.4 centimeters. That's how far you will pull the spring. All right. So that's all good. Now, the problem with what we have written earlier, f dx, when we integrate, is that formula can only be integrated, this thing here, can only be integrated from x1 to x2. It's equal to, we said it's equal to u1 minus u2 if the force is single valued. So for example, let me show you something where this will not work. Let's say I'm pulling the object this way with a force F. And let's say there is friction. In what direction will friction be? Well, if you're moving to the right, friction will be to the left. Let's say it's moving, so sliding, so it's force of kinetic friction. So the motion is this way. However, if you do the same situation, but the object is moving to the left, friction will act to the right. Force of friction will act to the right. So this is not going to work. So for example, for a spring, it works. The reason is, so here is a spring. This is the natural position of the spring. As long as you are on this end of the spring, the force is to the left. If you're on this end of the spring, the force is to the right. So we know the direction of the force of the spring as a function of x. We know its magnitude and we know its direction, both of them. Friction, on the other hand, let's say if you're here, I don't know what the direction of friction is. You have to tell me in what direction you are moving to figure out what the friction is. So friction will fail us here. Another thing, and we will call friction to be a non-conservative force. We'll see in a moment what that means. For a spring, the force made up its mind, so to speak. It has a definite magnitude and a definite direction at every point on the x-axis. Friction doesn't. Gravity. In what direction is gravity? Downward. How much is it? mg. So gravity has made up its mind, so it has a definite direction and a definite value at all positions on the y-axis, and therefore we can integrate it also once and for all, and we can associate a potential energy with gravity and a potential energy with a spring. With friction, on the other hand, we can't. We could calculate the work done by friction in going, let's say, from here to here. But if I want the work done by friction, if you're moving back and forth like a mass on a spring, what's the work done by friction? If you're going back and forth, you can't. You have to calculate the work done going this way, and then stop, and then do another integral when you're going this way because friction has changed its direction. For gravity, what's the work done by gravity? If you go up, on your way up, and then on your way down, gravity has a definite value at all points. It's always downward, and it has a certain magnitude. Namely, near the surface of the Earth, it's equal to mg. And so, we can associate a potential with it. So we cannot do this integral once and for all for friction, and so that spoils things. So we call friction a non-conservative force, and let me just show you, talk about that point one more time. So let me just erase here, and I want to emphasize that point again, and then I will come back to it next time. So the force of, again, we said the work done is the integral of from x1 to x2 of f dx, and that's equal to the change in kinetic energy, the kinetic energy at the end point minus the kinetic energy at the initial point. Okay. So we said if the force has what we call, if it's conservative, then it will have a definite magnitude and a direction at all points. It doesn't depend on the path, the direction you take. However, friction doesn't. So we can divide the forces that we have, the forces that you have, you can divide them into forces that are conservative and then forces that are non-conservative, like friction, right? Like friction. And so you can divide it into like that. So you say, so the work done will be the integral from x1 to x2 of f dx. So this will be the force, the work done by the conservative forces plus the x1 to x2. This is the work done by those non-conservative forces, such as friction, equal to K2 minus K1. The work done by the conservative forces, we can associate a potential energy with it, and we will call it U1 minus U2. And this will, plus, this part here, I'm going to call it the work done by the non-conservative forces, and that equals to K2 minus K1. And let me move everything to the other side so I get the work. This is the work done. Or actually, let me focus on this. Oh, did I erase? Nothing. Okay, so let me focus on this part. So let me move the U to there, and the U1 also. So we'll get the work done by the non-conservative forces will equal K2 plus U2. And then plus, or actually minus, U1 minus K1 minus U1 when you move it to the other side. And so you get the work done by the non-conservative forces would be K2 plus K1 plus U2 is called the total mechanical energy, E2. And then minus K1, so this becomes a minus K1 plus U1, which is the total mechanical energy at the beginning. And this is the work done by the non-conservative force. So here's what I'm saying. Let's say you have your total mechanical energy at the end, your mechanical energy at the beginning. If the mechanical energy at the end is less than the beginning, this will be a negative number, and so the work done by the non-conservative forces will be negative. It means you had friction and you have lost some mechanical energy. If the energy at the end, if your mechanical energy at the end is higher than the mechanical energy at the beginning, it means you had work done by non-conservative forces that was positive. Now, where does the energy go? The book discusses that very nicely, I think. early on in the chapter 9, in chapter 9. So it talks about heat loss or energy loss into heat. And so this conservation of energy, I should say, energy is always conserved. It's called the principle of conservation of energy. And when we say energy is not conserved, or mechanical energy is not conserved always, we mean that there is some loss to heat and other forms of energy. But if you include the energy due to the heat or in the heat, then the energy is always conserved. Always. You cannot not conserve energy. You can't. You cannot conserve or not conserve energy. You can always, energy is always conserved regardless of what you do. So in everyday life, when people say, hey, try to conserve energy by turning off your lights or not driving as much, what they mean is try to not take energy from a useful form that we can use readily to a form that we cannot use readily, meaning when you convert it into heat, it's hard to get the heat into useful work. And you talk about that in Physics 230. Okay? And so, what is heat? Well, heat, microscopically, you have atoms and molecules. If you, in everyday life, in mechanics like this class, we're not going to look at atoms and molecules, not at that scale. I have a pen, I'm not going to dig in and try to find what the molecules of the pen are doing. But if you look in, you will find that it consists of molecules and atoms, and those molecules and atoms, they are moving, and they have kinetic energy because they are moving around. And they also have potential energy, and that potential energy meaning it's in different forms of electrical energy and so on. Okay? So I hope that's clear, and in the next video I will do probably end of chapter examples from chapter 9, and I also have one more topic which is about power. So before I pause, let me just discuss quickly the concept of power, and then we will just stop this one and go to the end of chapter problems. I think this is one of those things that the more problems you do, the clearer it becomes. Okay. So power. Power. It's how quickly you can do work. How quickly is a force doing work? So you can walk upstairs really, really slowly, or you can walk upstairs really, really fast. Your potential energy, which is, we didn't really talk about it yet, gravitational potential energy, will be the same at the end point when you reach the same height. But doing it quick or slow is called power. So the power, it has the symbol P. It's the how quickly you can do work, dt of work. And we know that dw is f dx, and then dt here, and so it is the force times dx dt is velocity. It's the force times velocity. So if you apply a force and it's causing motion at a certain velocity, that is the work done by that force. So for example, let's say you have an object here, and let's say the mass is, let me just do an example from our book. Let's say you have an object, it's 300 kilograms. It's 300 kilograms. And let's say the coefficient of friction is mu k equal to 0.6. And let's say you're dragging it here at a velocity of 0.5 meters per second, right? I think that's the velocity here. It's 0.5 meters per second, yeah. So what you're doing is you're pulling it this way. That's the force. That is the force that you're pulling it. So as you pull it, why isn't it accelerating? But because there is friction. There is the force of friction this way, the force of kinetic friction this way. So since it's not accelerating, it means the two forces are equal, and so we get our force will equal to the force of kinetic friction, and it's equal to the coefficient of friction times the normal force, but the normal force is mg. That's the normal force. And so the power will be our force times the velocity, so it's mu k times mg times the velocity. So let's plug in the numbers and then talk about what happens. The mu k is 0.6, the mass is 300, g is 9.8, and what's the speed? It's 0.5. And let us get a number here. Get my number. Get 0.6 times 300 times 9.8 times 0.5. I got 882. Okay, 882 what? Well, it's work per unit of time. Work is in joules, and the time is in seconds, so it's joules per second. How many joules you give per second? Joules per second. And that's given the symbol W, 1 watt. So it is equal to 882 watts. W was 882 watts. And there is, while we're at it, there is the thing called the horsepower. 1 horsepower, 1 HP, is 746 watts. Look at that. So if a car engine is 1 horsepower, it means it can do 746 joules every second of work. It can do 746 joules of work every second. So to change this to horsepower, you multiply by 1 HP for every 746 watts. And so this becomes, that's a little bit more than a horsepower. So that's 1.18 HP. That's how many horsepower. All right, so in the next video, I'm going to talk about basically problems. I have 1 or 2 examples from the book that I would like to cover from within the chapter, and then we will talk about end of chapter problems. We'll do a few of those.